In this video, we are going to be solving this problem. I'm going to be doing the mechanism as well. So we just to do a quick overview here, molecule A in base, molecule A in the presence of a strong base is going to become an anion and be as such is a Michael donor to this molecule. This molecule is an alpha beta alpha. This is your carbonyl. This is alpha beta unsaturated carbonyl compound. And we're going to do the Michael attack here when we do the mechanism. After that, we're going to have a tautomerization step to get to this product. So we're going to do all that mechanism. Since we have two H's here, two acidic hydrogens, the second reaction right here in the presence of a base will be removing another hydrogen. Again, we'll do that mechanism. A second Michael attack will give you this. After that, we're going to be treating this molecule with sodium hydroxide and the hydrochloric acid. The idea of this reaction is an ester hydrolysis. So we're going to get here the carboxylic acid. And with heating, we're going to do a decarboxylation step to get to E. Now, going down below, going again to molecule C, treating that with sodium hydroxide and then hydrochloric acid, we're going to do another ester hydrolysis in this molecule. After heating, we're going to have a decarboxylation to get this molecule. Then this molecule, when treated with base, again, we're going to do an intramolecular Aldol reaction. And with heating, you're going to get the condensation product. So again, another alpha beta unsaturated compound, which treated with something that we're going to see in this video is going to give you is another Michael addition to get to the final product. So I'm going to copy the first two reagents to get started with the problem. So this is A. This is ethyl acetoacetate. And that, when treated with etoxide, strong base here, you're going to get one of the acidic hydrogens here. There's two. So now you're going to form this anion. This is a Michael donor. Michael donors stabilize enolates are excellent Michael donors. So this is what happened in this step. And now I'm going to copy here the Michael acceptor. So this is an alpha beta unsaturated ketone, and you're going to have the attack. The Michael attack is at the beta carbon. So the initial product would be the following. We are attaching here is a bond between this carbon and the beta, and then we're going to get the alpha carbon here. And next, we're going to have the carbonyl carbon is no longer a carbonyl. This is O negative. And the metal. And it says so here, and I say the quark cap. So we're going to get the enol, and I'm going to do the enol here. And this is it. Oh, I missed a double bond. Very important that have that. So again, so that we keep track of this. Now this is going to become, this is an enolate. This is an enol. Now we're going to have a tautomerization step to get to the final product. So, and typically this favors the keto form that the enol. Here we have now the substitution completed of the hydrogen by, now that we have the tautomerization step, we will have this. And this is the product that we wanted. Now this is molecule C. Let's write it down. And going up here, I'm going to do this reaction. You're treating this with base again. Let's remember that here we have an H. And so for that step, we're going to be removing another acidic hydrogen. So we're going to do ethoxide again, and we're going to remove this alpha hydrogen to form another anion. When you do so, and then to create again another stabilized enolate, now you have this negative here. And we say stabilized enolate because here or here, you can do resonance. And then you're showing a different color of the arrows. This is why we say there's a stabilized enolate. You can do resonance to that one side or to the other side, meaning the negative charge is spread. Same thing happens here. And this is we're going to the next step. So after removing the other hydrogen, we're going to get this product. All right. So then the other step that we have here is the Michael attack. So we're going to have another molecule of alpha beta unsaturated. Well, is actually a, it's not quite that molecule, but is, we're going to see that we have a good leaving group. So here we go. This is that. And now we're going to do, if you do the attack over here, and you get this, you're going to push the leaving group. This is like an SN2 attack, similar, but this carbon right here is allylic. In allylic substrates are great for both SN1 and SN2, and that's how that happened. And now we're going to have the replacement at the other H, and here we're going to copy the product after that happened. So this stays the same. And now we're going to have another group here. And this is going to be this one. I kind of squeeze it in. This is what we have after that attack in. Of course, you're going to be forming bromide. This is this product right here. Now it says this is that we were here. We'll explain that again. Second, removing anesthetic hydrogen in down. This is like an SN2 attack or an allylic bromide, added bromide. So we do that attack and we get that substitution. The second reaction here, another reaction that we have to get to product E is now we're going to do an ester hydrolysis. And with heating, we're going to do a decarboxylation. So now let's run this up. And again, this is, now notice that we're doing sodium hydroxide and, followed by, followed by HCl so that we get a carboxylic acid. And second step is heating, and we're going to do the decarboxylation. So let's go step by step. After is step one, ester hydrolysis under basic conditions in acid, we're going to remove this and form a carboxylic acid. Now, what I'm going to do to go to the decarboxylation step is I'm going to write the carboxylic acid a different way. So I've just rotated that. I did the hydrolysis, that is an OH, and then I rotated that. Everything else is going to be the same. Oh, that's supposed to be double bond. Yeah. With heating, so first step again, this is your carboxylic acid. So you did, that was negative, you protonated with HCl. Now we're going to do the decarboxylation step. For the decarboxylation step, what's going to happen, you're going to get this H, then you're going to form this. Notice that this is carbon dioxide that is going to, and we are going to write the immediate product here. But babe, after decarboxylation, we're going to get the following. This is gone, and now I'm going to write, this is this group. And now down below, I'm going to just copy the same thing. And now this is product 8. that way. Oh, they do move it. Okay. Hard to squeeze it in on one page. So this is that. Uh, E is this one here. All right. Now we are done with that part, and I'm gonna identify what is there. Well, this is E in that scheme that I showed you at the beginning. And this was A, and B was this molecule. So I'm just identifying that. Product C then is this. Yeah, this is C. I have it already identified. And now I have a, so after the second, say, substitution of the acidic hydrogen, and then again, ester hydrolysis and decarboxylation, we get here. Now we're done with that path, and then I want to go from C to the final molecule here. That involves again ester hydrolysis, decarboxylation, then an aldol reaction. Aldol in with heating, we're gonna get the aldol condensation product. This time the aldol is going to be intramolecular. Okay, so I'm gonna grab another piece of paper to get this. And now let's work on that part. And it will be, I'm copying that again. We're going to repeat the process of the ester hydrolysis and decarboxylation. So we're going to have this. And again, treating it with, if you just said the hydrolysis, if you want to go step by step after treating that with NaOH, this two, that will become a carboxylate. And then, of course, you treat it with hydrochloric acid. There's a step here, then, and then that. And you're going to get here OH. And this time, again, I'm going to do what I did before. I'm going to rotate this so that I get now OH here and that. That will facilitate to do the drawing of decarboxylation step. The decarboxylation step, similar to what we did before, is this. And now we're doing this is going. So, and that is step minus carbon dioxide. I'm going to form minus carbon dioxide. Let's do it here. Okay, now I have, this is going to be OH. This is going to be a double bond. And now I'm going to have all of that. So after this one, and here is this carbon. Let me just highlight it, and then we're gonna have 1, 2, 1, 2, and then carbonyl group. And as you hear, this is an enol. We can tautomerize that, and the tautomer going to be the compound that we have here. So we're now in the next box. That. So this is the polymer step. And what we have here in the, this is that. And now we're going to treat it with base, again, sodium hydroxide in this is an ether in the MCl. So this step 1 is an intramolecular aldol reaction. With heating, we're going to do a dehydration to get the aldol condensation product. So let's write up what are the reagents again. We're going to do, it says here, sodium hydroxide, and that was diethyl ether, and then says HCl, and last step we're going to do heating. Well, Okay, I'm gonna do the heating in the next step. So I'm gonna do it like step by step for you guys. So the first thing that we're gonna do with that is to form, gonna remove, this is again an Aldol reaction, but this is intramolecular. So I'm going to do remove one of the acidic hydrogens here. And what's going to happen is an intramolecular attack. And let's see, what is important to notice is this is happening when you can form rings of 5 and 6 members. So here you have 1, 2, 3, 4, 5, and 6. And then you have a metal attached to where the O negative is going to be. So I'm going to draw a 6-member ring. Here is. So this carbon is going to be now attached to O negative into a metal, as you can see. And here is that. So following the numbers, if we did say that I have numbered this one like that, so we can follow up. 1, 2, 3, 4, 5, 6. These are the numbers that I did. So if this was 6, then 5, 2, 3, and yeah, that's 2. Yeah. And so that's my product. This says, well, after HCl, you're gonna get the aldol. Oh, I'm sorry that I didn't move it. I'm gonna have to repeat myself. So intermolecular attack, that was O negative, that had a metal, and this is my 6-member ring. And so next, after you do the HCl, of course, you are going to get this OH, and this is that. And now upon heating, you're going to do a dehydration step, and you're going to form an alpha beta unsaturated ketone. And that is a good Michael acceptor, alpha beta. This is alpha beta unsaturated ketone. Now what we're going to use to get to the final product, let's analyze what we have in the final product. Notice that I am here, and what I have, my final product, I'm going to draw the final product we want to do. So that's my target molecule is. I have a carbonyl here, and I have methyl and ethyl. So that's what I want to go. So right here, this is the aldol and the aldol condensation. So after dehydration, I'm going to write here minus water. So how do we get here? This is a Michael acceptor. And what we're going to use here is a Gilman reagent. So this Gilman, I'm going to do diethyl. This is going to be negative. Counter ion is plus. So this is a source of, say, this negative, or you can do this. That's a source. Again, this is the Gilman reagent, and uh, this is different to the Grignard reagent. When we use Grignard, the attack is at the carbonyl group. When we use Gilman, the attack is always at the beta carbon. So Gilmans are good Michael donors. And what we have here is then the attack the beta carbon. So I'm going to continue that arrow. When you do that, we need to, if you add that here, you need to move those and move that. So my molecule now is going to look like this. I'm going to have methyl and ethyl that I just added with the Gilman, and I'm close to that. Now I'm going to have a double bond here and an O negative. And that after you treat it with, so this is, I have a box actually here. So I need to complete the reagents. Once I have this, I need to complete the reagent. So my first reagent is this. which is going to be in this box. So how do I get from the Aldol condensation to that is a reagent that I need to complete. So this is first step is Gilman, and then I'm going to do an acidic workup to get the, now I have what I need for my target, and I'm gonna get this is gonna become OH. And the final step is simply a tautomerization step. That's the tautomer. Okay, right. So we have done, I have used 2 pages to explain that one. Okay, so we did recap. The first step here was forming a Michael donor, Michael attack. So conjugated addition is another word for that. We did this product is the enolate with upon acidic workup. This is the enol. That is the ketone form. We have another acidic hydrogen. We remove that with sodium hydroxide, and here is an attack. This is like an SN2 attack over analytic substrate. And now you have this. And this step right here was the Ester hydrolysis that will become OH after treating with HCl. And this is rotating it. Decarboxylation, so minus carbon dioxide, we get you the first product Eve. And the other pathway that we did is starting here. We did the ester hydrolysis, that's carboxylate, with HCl. You do the protonation, but I rotated this so that I have the actual conformation to do the decarboxylation. That is now OH here, but you will. Oh, I'm having an extra bond actually here. I'm glad that I did the recap. So here is your enol, and that's the tautomerization. Once we have here, this condition is to do an internal and intramolecular Aldol reaction. So removing that, you will form a 6-member ring. And this is upon acidic workup, you get this compound with that's the aldol product. But with heat, you get the dehydration step, so alpha beta unsaturated ketone. And this is a great Michael acceptor. We will use Gilman to introduce the ethyl group that I have here in the target. When we do that attack, moving those electrons over, you get the enolate, say enol upon acidic workup, and finally a tautomerization step. Okay.